Good afternoon, ladies and gentlemen. Thank you for joining us today at the What Now Technical Talk, where we talk today on lightning, protection of structures, and how to do it wrong. I am Minx Avrabos, the managing editor of the What Now magazine. Just before we carry on with our program, I just have a few webinar considerations for you. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of the presentation will be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the Events drop-down menu in the section Past Events and Webinars. This page is updated regularly, so ensure you check back as often as possible for new uploads and subscribe to our YouTube channel for more uploads. A certificate of attendance will be issued a few weeks after this webinar, once we have received the CPD validation number from EXA. I now introduce you to our presenter for today, is Professor Chandima Gomes. He is the Director of Center of Excellence on High Voltage Engineering at Wits. He is also the Chair at Eskom Power Plant Engineering Institute, HVAC, and the Director, Center of Excellence on High Voltage Engineering at Wits. I repeated myself, sorry. He's a chartered engineer, a professional physicist in South Africa, and a fellow of the South African Institute of Electrical Engineers. He was a senior advisor to the National Lightning Safety Institution in the US, the chief advisor to African Centers for Lightning and Electromagnetics based in Uganda and USA, and an advisor mentor to several other national lightning research awareness centers in a few countries. Chandima has conducted over 120 training programs on lightning protection and electrical safety in 12 countries so far. I hand you now over to Professor Gomes.
Thank you very much, Minx, for the very nice introduction. And good day, ladies and gentlemen. I think for some of you it is morning, for some it is evening, and for some it is daytime. So today we are going to discuss something interesting, lightning protection, how to do it wrong. Well, rather awkward title, but let us see how knowing how to do it wrong is going to help us doing that right. And let me start with the very basics. And lightning protection has basically two parts: protection of structures and protection of equipment. Together we call them lightning protection total solution. And if you do it right, a structural protection system consists of two parts: the external protection, which consists of the air termination which intercepts with a lightning strike, then the down conductors that conduct the current from top to bottom of the structure and then disperse the lightning current into earth, which is done by the earthing system. And apart from that, all parts which are conducting and close to the lightning protection system should either be bonded electrically to the lightning protection system or separated by a certain specified distance, which can be calculated according to IEC 623053, the apex standard in lightning protection in the world. If I put everything in one picture, it is this. We need air termination, and you can see that according to this picture, this is purposely done in this way. These air terminations are smaller than the objects at the top of the building, which is wrong. And just when we consider air termination, we get the idea of vertical metal conductors. But there is one very important thing about these air terminations: they should always cover whatever to be protected on the top of the building. So we'll start with something wrong, and to know something wrong is one of the most right things. And then if you do it right, the concept of lightning protection is this. Very simply, it is the interception of downward lightning leader with the protection system and safely passing the current into ground. So I repeat it, if you do it right, then the concept of lightning protection is whenever there is a downward lightning flash, which we call the step leader, and when it is around 50-100 meters, we implement a lightning protection system to any structure that will send a streamer which will intercept with the step leader. It actually invites the lightning to that particular system, which we call the lightning protection system, and safely pass the lightning current to ground. So let me show it with a very simple animation. What you have seen is, in the absence of a lightning protection system, any part of a building can send this answering leader towards the step leader and intercept with the lightning step leader. Then we say that that object or that structure is lightning struck. And when one building get lightning struck, what we do not know, and that goes unnoticed, is that there are attempted leaders, attempted invitations from many buildings in the surrounding, and they send answering leaders which are unsuccessful in meeting the step leader and die out. And when we have a lightning protection system in the building, okay, before unprotected parts of the building send an answering leader to the step leader, one from the lightning protection system will interact with the step leader, and the current is bypassed, or current is passed into the ground. Okay, now let me say that there is a lightning which, in the absence of any lightning protection systems, which goes to the right hand side building. And let me say that our building of concern is what is in the left hand side. So this lightning goes to the right hand side building, which is not of our concern. It may be a neighbor. Now we see that instead of the previous lightning protection system, now we have a very tall air termination and one down conductor. This is a wrong installation. Now see what happens when that same lightning step leader comes. Okay, now because of the height of this air termination, the step leader, instead of going to the neighbor's building, may come to our building of concern. Now we have to be a little careful and think about few points that happens if a lightning current passes through our lightning protection system. Although we say that the lightning protection system protects our building, there is always a risk. There is always a risk. There is a risk of arcing. there is a risk of touch potential, there is a risk of step potential, and there is always uh, not only a risk, there is always a strong emission of electromagnetic radiation. So therefore, we always try to make sure that if a lightning step leader is going to attach with our building, then the lightning protection system will interact with that lightning, but not a lightning which would have gone to somebody else's building that I'm going to get into my building. So the what you see in this slide is a wrong concept of lightning protection. Therefore, the IEC standards have been developed optimizing the ability of the lightning protection system to interact only with a lightning step leader which would have been interacted with the building in the absence of the lightning protection system. Hope that you got the idea clearly. Now we go to a little bit of lightning the characteristics. I'm not going to any details because this is not about lightning, it's about lightning protection. Now what you see is a very typical lightning current waveform. This is somewhat like a double exponential waveform, but it is little more complicated than or complex than a double exponential waveform. Usually we represent the lightning current by Heidler waveform, a so-called Heidler waveform, and this is the Heidler waveform that you see. One important thing about this lightning waveform is that typically, when the lightning current is around 80% of the peak value, we reach the maximum di by dt. What is di by dt? It is the rate of change of current with respect to time. And in the next slide, you will find that when we calculate the voltage due to the lightning current, the di by dt play a very important and significant role. So therefore, the 80% IP is usually the time at which we get the maximum voltage. Let's go to the next slide. Now let's imagine that there is a structure, maybe a tree, maybe a copper tape, maybe a brick building, anything. If say that it is 10 meter high, if lightning strike the top of this structure, then when the lightning current flows along the structure, there will be a potential difference or potential gradient, as if I say it correctly, develops from the lowest point where we consider the potential to be 0 up to the highest point. And if we want to calculate the voltage across this component or this object, which we can consider as a resistance and inductance combined series component, then the voltage is given by IR plus LDI by DTF. Actually, I'm not going to any mathematics, just only this equation, which is the very basics of electrical engineering or electricity, I may say, not even engineering. Now, if I do a small calculation, imagine that our object is a brick column, a bad conductor. Usually the resistance can be about 10 to the power 5 ohms per meter. This is not resistivity, okay? It is in 1 meter of the column can have 10 to the power 5 ohms. So it is ohms per meter. Then the inductance could be like 2 microhenries per meter. And if I consider negative subsequent strokes, lightning has a first stroke, first subsequent stroke, both in negative lightning, then positive lightning. But usually the negative lightning has quite high di by dt values, and negative subsequent strokes has the highest di by dt value. So if I take the mean values, then the peak current is about 12 kiloamperes and di by dt is about 40 kiloamperes per microsecond at the peak. These values are from South African databases. And then if I apply these values into the above equation, we get this. There will be an enormous voltage, 9.6 gigavolts, due to the resistive component, and rather moderate value compared to the resistive component due to the inductive component, 800 kilovolts, okay, in this 10-meter long structure. Now you will understand that when lightning strikes a bad conductor, such a large voltage is developed. So the result would be sometimes arcing, sometimes explosions, and it can be many hazards. Okay, now this slide shows you the same calculation, but now I'm considering a good conductor like a copper tape, where the resistance is about 10 to the power minus 4 ohms per meter, and the inductance more or less the same. When I do the same calculation, now I will get that V is 9.6 volts, extremely low compared to the other values. But that moderately high 800 kilovolts due to the LDI by dt is still there. This is something that you should not forget, because when you are designing a lightning protection system, make sure that you have an understanding. Even with a copper conductor at a 10-meter height, you can have something like 800 kV, or at 1 meter 80 kilovolts. Don't forget that this is for the mean value, not extreme values. Okay, so the actual value in some cases of lightning can be much higher. Okay, if you do it right, I'm still in the rightly doing mode. The lightning protection is done under 4 classes. Level 1 is the highest and level 4 is the lowest. And the IEC standard gives for each level of protection, there is a maximum current and a minimum current. What is the meaning of the maximum current? That will give you an idea of what is the maximum current in the event of a lightning strike the lightning protection system can withstand without thermal or mechanical failure. So for an example, if you go to the level 1 protection, then the system can withstand up to 200 kiloamperes. But on the other hand, if you go for an example to class 3 or level 3 protection, it can withstand only 100 kiloamperes. What does this minimum value mean? It means what is the minimum current of a lightning that the lightning protection system can intercept with. So in other words, if the lightning current is very low, there is a probability that the lightning protection system will miss the step leader, and the step leader can get attached to an unprotected part of the building. So the table below shows the percentages of such success in the case of lightning protection systems. For an example, if you go to the maximum lightning current case, if you go to level 4 protection, 95% of the cases, the current will be less than the value speculated or the value given for level 4 protection in the lightning current. So there is a chance of 5% of failure. If you go to the minimum case level 4 protection, just as an example, there is a 16% probability of the step leader is missed or bypassing the lightning protection system. Let me show you this graphically or with a small animation. Now consider a step leader that will give rise to a return stroke of 100 kiloamperes. Okay, now you will see that just like in the previous case, even from the same building, there can be unsuccessful leaders coming to meet the step leader, but usually if the current of the lightning is very high, that means it is bringing very large amount of charge. In turn, a very large amount of charge brought down will give rise to a very large electric field at the tips of the lightning protection system. Therefore, a streamer will be started from the lightning protection system much earlier in the case of very large current lightning that is coming towards your building. But on the other hand, if the lightning current is quite small, in turn that means the lightning is bringing rather small charge, so that the electric field enhancement at the tip of the electrodes or at the tip of the air termination will be small. So the result would be this. So as the streamer is now small, now slower to be incepted, by the time the streamer from the lightning protection system starts propagating, the lightning has bypassed that level and get attached to another upward streamer coming from an unprotected part of the building. So this is what the minimum current means. Okay, still in the the correct way of doing lightning, there are 3 ways of implementing the termination: mesh method, protective angle method, and rolling sphere method. And today's presentation is not about any of this. Actually, we are starting our story at this point: how to do it wrong. Now, if you do your lightning protection in the wrong way, there are 2 methods or 2 concepts in the market. One is, instead of the word interception, now they use the word attraction. Attraction of downward lightning leader with the protection system and safely passing the current into ground. The other one is dissipation of the lightning current. The dissipation of the charge of the downward lightning leader, that is one story, or repelling of the lightning leader away from the protection system. We go into that at last. And this attraction of downward lightning leader is basically done through something called the early streamer emission devices, where a virtual height of the rod is considered. let me explain that later. Whereas in a normal lightning protection system, which we call Franklin rod, only the physical height of the rod is considered. And in this other case, no standard in the world, not a single standard, international or national in the world, has accepted this theory or this concept, but still the market is now getting flooded with these products. Okay, let's first discuss about this so-called ESC technology. What they say is this: consider that you have a 1 meter rod, both a normal rod and a so-called ESC rod. In the case of ESC rod, they say that although the physical height is this much, there is a virtual height of that much. And how do they say that there is such a big virtual height? This is the theory that they put forward. And first, I'm giving you some physics. This is correct physics. And if you have a rod plane gap where, say for an example, there is a plate on top of this system which is negatively charged. Therefore, this rod, which is earth, become positively charged. So now what happened is that the air molecules in the vicinity of the tip of this electrode get ionized, and the electrons will be attracted into the positively charged electrodes, and those electrons will flow into earth. So therefore, if you have a Rogowski coil and an oscilloscope connected to this electrode, what you will find is this: suddenly when you apply the voltage at the upper electrode, there is an inrush of electrons which will cover the electrode for a very short period, and then these electrons will be going into the earth, and the positive charge, the space charge developed, will be there for a very short time in the microsecond region, and then it will gradually move away. And after some time, the space charge disappears and another current pulse will be observed, so that when it disappears, the electrode is exposed to the upper negative electrode, so that another inrush of electrons will happen. So therefore, if you look at the oscilloscope, this is what you will see. There are pulsating current in the electrode. The simple reason is that in the presence of the space charge, the ionization happens, stops, and so on. Hope that you understand this. Now, it is argued that this delay slows down the streamer initiation, and ESC people say that they can eliminate this space charge development, the inrush or rapid space charge development, so that the streamer will be started at a much earlier stage than in a normal rod. That's where the early streamer term comes from. And this picture shows you very clearly this phenomenon. So this is an experiment reported by one of the ESC manufacturers. I have made it a little clearer. If you have a Franklin rod, and then in the upper electrode, if you apply a certain high voltage, what you will see is this: with time, you will see brushes of corona charge coming up, and after some time, the corona charge will turn into a continuous streamer. But the ESC people say that if you keep their rod instead, the propagation of the streamer will start from almost the right beginning and happens all the way. So therefore they say that there is a time advancement or time advantage of the ESC rod in comparison with the Franklin rod, which you can very clearly see that it is TFR minus TESE. So that they develop the concept in such a way that they calculate this time advantage, then multiply the time advantage by the speed of the answering leader. This is a very important point which we will discuss at a later stage. And ESC vendors arbitrarily assume that the speed is 10 to the power 6 meters per second. I'm sorry, the unit is missing there. It should be 1 into 10 to the power 6 meters per second. And then what they do is that they consider that the height of the air terminal, if it is having a physical height of 1 meter, they add that length advantage into the physical height, so that then finally they calculate an area of protection, or rather volume of protection, given by this equation, where RP is the radius of the volume at the reference plane, which usually is a very, very large area or very, very large volume compared to the protected volume given by the physical height of the air terminal. So where does this concept being triggered? Now, actually, the lightning protection system, the concept that we are using, was developed way back in the Benjamin Franklin's time, about 300 years ago. And then at that time, I think copper and metals were quite cheap. But in the 1970s, suddenly there was a very large spike in the price of copper, so that people looked for some new ways of reducing the amount of copper. And then some people started adopting a method which has been practicing since about 1920s. People thought that by putting a little bit of radioactive element on the air termination, they can increase the effectiveness of the streamer, or the streamer can be initiated faster. And several radioactive materials were used for that. And then the ESC people, so later on they were called ESC people, but those people who were thinking about the concept of early stream emission, they started adopting this radioactive material technology and said that, okay, we are going to enhance the streamer initiation by keeping a little bit of radioactive materials on the top of the air terminal. So that technology was not developed in 70s. It was started in the practice around 1920s, but in 1970s it became retermed or reterminologied as early stream emission. And then, due to various health risks, the radioactive type ESCs were banned, and then many other technologies surfaced, and that gave rise to many types of ESC devices, and each one is sorry, different from the other due to various factors like radioactive source, electronic device, piezoelectric effect, and so on. So these are few of those. And now the difference they introduced into the design of lightning protection technology is that as the ESC rod has a much higher physical height, what they said is that if they can have one ESC rod usually put at the top of the building, they can replace all other air termination. So what can be done with a very complex system of air terminations can be achieved according to the ESC manufacturers by one air termination and one down conductor in most of the cases. And then they said that about 20 meters there should be more than one conductor and so on. But up to 20 meters they allow, even in the present standards, they allow one conductor under certain conditions. Now, whereas many nations and even the international standards refuse recommending this so-called new technology, in 1995, the French standard and within few months, the Spanish standards adapted this technology, and both were updated in 2011. And apart from that, and maybe one or two Latin American standards, the rest of the world did not recommend this technology in their national standards, and also it is not recommended by the IEC standards. Now, this is they then developed certain ways of calculating the protective area. One is this collection volume method, which was developed for something else, and the ESC people started adapting it for their purpose. Okay, now, despite the claims by the ESC people, we have so many issues with this methodology. Now, to start with, let's assume that French standard is correct. I'm repeating, we start saying that, okay, let's say that French standard is correct and French and Spanish standards are correct. But still there is a problem. Now, up to about 20 meters, they recommend one down conductor. This is one catch point or attractive points of ESC technology, because they say just one down conductor, so it is very convenient for the installer as well as the lightning protection seeker. But now we have seen that even if we consider a value like 50 kiloamperes per microsecond di by dt, as you have seen earlier, very close to the mean value, 10 meter, you have seen that even 10 meter can have a rather large voltage. So if it is 20 meters, the voltage can be like 2 megavolts and in that range. Don't forget that when we are considering the calculation, it is not the height of the building comes to the picture, because when you are having a down conductor, there are so many bends, horizontal paths going from edge of the building to the air termination. So the real length of the conductor may be several percentage, say like 20-30% higher than the length of the or height of the building. So therefore, what you will see is that there is a fat chance of a large voltage drop having along the conductor, and towards the top of the building, the voltage can be extremely high. So in plain words, even if the air termination attracts the step lead as the ESC vendors claim, there can be arcing. So this picture I have taken from, it's from Sri Lanka, a very large Buddhist monument. It has an ESC rod to protect the monument, and somewhere around 2006 or 2007, there was a lightning strike into this suspected lightning strike, where there was a huge damage observed around the neck of the statue. What has happened was the masonry has been destroyed, and we assume that the lightning current has passed into the steel structure because of the very high potential difference between the down conductor, the single down conductor, and the steel structure, which is essentially grounded. This is seen in many buildings that we have discussed or we have inspected so far. And issue number 2, if lightning comes from a side, there is, and if it bypasses, especially low current lightning, then there are no other down conductors. So the same thing happens when a tree is struck by lightning, the current can jump into the building. Issue number 3, EHC rods are very expensive. So at the first place, ESC technology came because copper is very expensive. But if the ESC rod itself is very expensive, then the primary objective of introducing ESC technology is lost. Okay, now we come back to our assumption. We assume that the French standards is correct, but do French-Spanish standards have a scientific base? Now we are going to the biggest issue of the ESC technology, which totally collapses at this point. Now the ESC manufacturers adopt an arbitrary value of 10 to the power 6 meters per second as the speed of the answering leader. And can you remember that when they are calculating the time advantage, they simply calculate the time difference into the speed of the answering leader, and they take it as 10 to the power 6. But the recent studies, even done by our own research team at Wits University, it has been shown that the speed is in the order of 10 to the power 4 meters per second, because in 1995 they did not have any technology, but now we have very high speed cameras. So now we have the technology to measure this value, and so it is 100 times less. What does that mean? If they say that the ESC rod has 150 meter virtual height, actually it is 1.5 meters. So what is the purpose of spending thousands of rands, sometimes even 100,000 rands for several ESC rods to have a 1.5 meter advantage? You can just have a 1.5 meter copper rod. So finally, when the vendors of ESC say that they have a protection volume of that much, the scientists say that it is this much, unfortunately. And issue 5, according to the French standards, the testing for an ESC device should be done with a rod plane gap of 1 meter. Actually, the gap is 2 meters, but when you put the rod, which can be about 1 meter, then the gap length actually reduces to 1 meter, not even 2 meters. Now the question is, can we extrapolate the results that we get from a 1 meter gap breakdown into many meters or many 100 meters phenomena in nature? Okay, now what is the real protection radius of ESC? This is a case, and most of these photographs I am showing are from Malaysia, and the owner of these photographs, the person who published these photographs, is Mr. Hartono. So I have to be very thankful to Mr. Hartono for his untiring work in getting the evidence to show that the ESC technology does not work or it fails. Now, this is one case, an ESC rod, and so according to the calculations, it can protect the whole building, but you can see that the lightning has struck just maybe about 10 meters away. Then I'm going to show you many such cases. This is the famous Putrajaya Mosque in Malaysia, and it has a ESC rod, but the lightning has struck the building many times just underneath the ESC rod. And this is another case. Another example. Now you see that according to the calculation, that ESC rod on the left-hand side can protect even the neighbor's building, but it was struck by lightning. So don't believe when your neighbor says that, hey guys, I'm protecting your building as well, see how generous I am. Don't believe them. They may have been taken for a ride by the ESC vendors, and they are taking a ride on you. And also we see many cases where there is a problem of mechanical stability of ESC rods because they have very heavy elements at the top. And in the one in the middle, most probably this was containing radioactive material, and this damage shows means that radioactive material may have gone to the ground level and exposed to the human activities. Okay, now I'm going to a very important point. Whether there is ESC or no ESC, you can see that in the event of lightning, what are the points that lightning mostly love to strike? Go ahead with these, or just check these photographs. I'm not explaining anything. It is self-explanatory. So what you can see is that lightning love to be intercepted at corners and edges of buildings. What we have observed is that more than 90% of lightning strike damages occurred at upper corners and ridges of buildings. Less than 5% occurred on vertical edges below the top, like that. And less than 1% occurred on flat surfaces, either horizontal or vertical. So with this observation, what we can say is that protect edges and corners. Protect edges and corners. Unfortunately, if you give your lightning protection to a ESC vendor, if you keep your fate in their hands, they will put an ESC air terminal at the very middle of the building, because then only they can have the highest coverage, as they say. Okay, that's about the ESC technology and their failure. So now you see that how you can do it wrong when it comes to the lightning protection system technologies. And now we are going to what the second part or second wrongdoing that I have shown you earlier. Now there are things like lightning eliminating systems, lightning dissipation arrays, SLE, resistive air terminal. So many terminologies are used by the vendors to tell that they have a system which can repel lightning. They can repel lightning. At the beginning, they said that their system can dissipate or neutralize the step leader, and even some people said that neutralize the cloud. Later on, they changed their tone or changed their story into another version where they said that this system will cover the building with space charge, so that the step leader coming down looking at the building sees the space charge and it will go to some other place. So I mean, as a story, this is a wonderful thing, but the problem is, this is what they say: a large amount of space charge are rapidly generated from this array in the presence of step leader. Either these space charge neutralize the opposite charge in the step leader, or space charge cloud repels the step leader. Exactly what I said. The concept sounds really good, but there are some grave doubts about this concept, which totally contradicts with the accepted scientific knowledge. Actually, what I say is that the theory put forward by these people can be rejected or negated by even a high school student. Now, space charge is not like a bucket of sand that somebody takes to the top of the air terminal and throws out so that it neutralizes the step leader. What actually the space charge is, whenever there is a high electric field at especially at a metal part, then the air molecules around will be neutralized. It will be ionized, just like what I have shown in the case of ESC, the ESC experiments. And what happens is that whenever there is a step leader, this blue color line represents the step leader. When it is around, there will be a very high electric field around the tip of the air terminal, so that now either electron starts getting into the air terminal because the air molecules are ionized. Say for an example, we are getting a negative lightning with say a negative step leader comes down. So the negative step leader will generate a very large positive electric field, oppositely charged electric field in the air terminal, so that the electrons will be repelled from the air molecules, and those repelled air molecules will become space charged. The electron repelled air molecules become space charged, positive space charge, which will go towards the step leader, whereas those electrons collected by the air terminal will flow into ground. You can see it. Okay. Now, in the same way, if a positive step leader comes, the air molecules will get additional electrons, or electrons will be repelled from the air molecules, and those repelled air molecules will go towards the positive step leader, whereas now the electrons will come from ground level, from earth to the tip of the air terminal, so that the blue color line, the direction of the blue color line will now be opposite. It will go from bottom to top if those blue color dotted lines will reflect or represent electron flow. Okay, now you can very simply see that whenever there is a step lead, imagine that I have a device which will generate huge amount of space charge. What does that mean? My device is ionizing so much air molecules that these air molecules will now move towards the step leader, the positively charged air molecules, whereas the electrons will flow along the air termination into ground. So that anyway, this is what happens in the event of a lightning step leader and a lightning protection system. So that definitely that lightning current will finally flow through the air termination. Okay. And then one other point. In the recent times, some people came out with this type of large spiked device, which is not even earthed. They just put it on the top of the building and say that the building is safe. No lightning is going to strike that. Now you can see that this is the most dangerous lightning protection system that you can add up. It is much more dangerous than not having an lightning protection system, because when you have it at the top, now what happens is that the space charge development is very slow now, because those electrons either coming into the air terminal or going from the air terminal now goes through a streamer, self-ionized streamer, going from top of the building to the bottom. But in this case, if that point is struck by lightning, the lightning current has no good path to flow into the ground, so it will arc all over. And this is the problem of this system. That's why it is not accepted in any standard in the world. I'm repeating this technology: lightning repeller, lightning eliminator, SLE, whatever the name it is given, it is not accepted by any standard in the world. Final word. Now some people, both ESC people and these people, the lightning eliminator people, they are playing a big trick to make people, I mean the people unaware of lightning protection being caught by a certain trick. This is what they do. Now, if you go to the IEC standards, they say that, as I told you earlier, there is a maximum current, there is a certain maximum current the air termination can withstand. So there is a certain test for that. For an example, if you are providing an air termination or you are selling an air termination system, that air termination system should be tested by applying that maximum current, say for an example 100 kiloamperes, 10 by 350 waveform into the air terminal, and show, you have to get a certification that the air terminal has mechanical and thermal stability under that current, 100 kiloampere current. So this certification has nothing to do with the ability of that air terminal to repel or attract current, to either repel or attract current. However, what these vendors do is they go to a testing facility, say for an example, they go to SAIEE and ask their rod to be tested for this maximum current testing. And the SAIEE do the testing because they have to do that. It is according to the IEC standard, and say that SAIEE certifies that this rod can withstand 100 kiloampere current for the mechanical and thermal stability. And then these people will show this certificate to the people and say that, you see, even SAIEE under IEC 62305 has certified our product. This is done by each and every vendor that I have come across. This is wrong. And whenever they say that this is according to IEC standards or SANS or any other country standard, apart from French and Spanish standards, ask what is the test that has been done for which they have got the certificate. I think this slide I will just go out of, because my time is over. It is 2 o'clock sharp now. Thank you very much for listening to my presentation, and it is the Q&A, and over to Minx.
Thank you very much, Professor Gomes. I was just going to take a few questions. Our first question is from Malindu Mihiranga, who's asking, what are the differences between single point and multi-point conventional air terminal?
Okay. Now, when it comes to the IEC standards, it does not make any reference to the number of points or even the shape of the point. So IEC standards just say that there should be an air termination. If it is a vertical rod, what is the cross-sectional area, and what would be the length of the conductor to get a certain area of protection or volume of protection. Apart from that, it does not say anything about the tip shape of the air terminal. But if I come to the scientific level, the research level, what I can say is this. We know that sharper the point in the presence of an electric field has the greatest, or the higher, the sharper the point, higher the electric field enhancement. So that means one would expect, when there is a sharp point, a streamer to be incepted or started quite effectively. Then somebody can argue that when you have many points, the streamer initiation may be even better. But some research done in the last 20 years have shown that the effectiveness of initiating a streamer is having an optimum value depending on the tip radius. So when you change the tip radius from large values, that means a blunt tip, to a very small value, which is a sharp tip, you will find that in the middle there is a certain optimal tip radius, I can't remember that value, where the streamer initiation is the best. However, no quantitative studies have been done in this regard so far to make that findings to be included in the standards. That's what I can say about it.
Thank you very much, Professor. Our next question is from Pascal Motsuasele. He's asking, has technology not advanced significantly over the years to bring the radioactive ESE air terminations to an acceptable level of health risk? He mentions, I think you covered this on slide 29 or 30, but I couldn't follow.
What is his question?
Has technology not advanced significantly over the years to bring the radioactive ESE air terminations to an acceptable level of health risk?
Okay, now the thing is that radioactive air termination, this technology is now obsolete, I may say, because people have developed many. At the first place, I say that ESE technology is wrong. That's what the whole purpose of this presentation. Now, the earliest generation of ESC technology was the radioactive material. And then, due to various health concerns, the radioactive air terminations have been banned in many countries. If somebody says that they have developed some technology so that the health risk has been reduced, that's just a claim, because nobody has accepted that, either scientifically or under any standards. So as far as I know, it is not used now in many countries because it is legally banned in many countries. And then if somebody says that it is now developed to reduce the health risks, I don't know up to what extent it is accepted by the standard committees in one side. On the other side, as a ESC rod, I don't know how effective it or how much it is accepted even in French and Spanish standards, so that they have done the testing or not. But at international level, it is not accepted. That's what I have to say.
Thank you, Professor. Our next question is from Stuart Thompson. He's asking, why is the peak lightning current assumed to be the same for a brick building and a copper down conductor?
No, actually, in my example, I took a certain lightning current, and I assumed that the same lightning current is injected into a copper tape and also a brick building. So without injecting the same lightning current into these two cases, I cannot compare the voltage developed in the two cases. So I don't know exactly what he tried to clarify from this equation, because it's very simple. That I'm going to tell you that when the same current amplitude, same current waveform is injected into a brick building, a brick column and a copper conductor, the voltage drop along the two which are having the same height is totally different. So that is the idea.
I see, thank you. And another question from Stuart Thompson is asking, what is the generally accepted maximum earth resistance for an LPS?
Okay, now this question is interesting, because at the very first place, for a lightning protection system, earth resistance is a meaningless term. We have to talk about earth impedance. But unfortunately, earth impedance measuring devices are quite expensive and also quite complex. Therefore, the standard committees are compelled to have a resistance, low frequency resistance limitation value in the standards for lightning protection systems. Now, again, don't forget that if you go to IEC 623.053, you will find that they're talking about two lightning protection earthing systems. One is type A, one is type B, where the length or dimensions of the electrodes according to the level of protection and the soil resistivity have been specified. And they say that if these criteria cannot be followed due to any reasonable any reason which is reasonable, then they can achieve a limiting earth resistance of 10 ohms. Okay, that is the IEC standard value. However, this earth resistance value depends on what standard and also what application you are going to use. For an example, if you go to some defense standards, they say that the earth resistance of magazines should be less than 1 ohm. In some cases, for the communication towers, there are several national standards I know specify 3 ohms. And in some cases, it goes to 5 ohms. So people give different values, giving various reasons. So therefore, I cannot tell exactly in general what is the value. What I can say is that according to IEC 623.053, they specify a below 10 ohm resistance. However, what the advice I can give you is that as lightning is a transient phenomena, always try to have a distributed earthing system rather than concentrating only on the low frequency resistance value. Thank you.
Thank you, Prof. Our next question is from Ukhatla Lefawani. He says, would you say there is a case for ESE technology, in inverted commas, to provide effective lightning protection to especially narrow structures like, for example, cell phone towers?
His question is, can ESC give protection to cell phone towers?
Yeah, he says, is there a case for ESE technology to provide effective lightning protection to narrow structures?
Okay, my dear, if you take a metal telephone tower, the tower itself is a good lightning conductor. Why do you need another very fancy, lucrative air termination system spending several tens of thousands rands? So my point is that you can have, if you want an air terminal to cover the antenna structures, then just have a copper rod. Why do you go to ESC? It's totally useless. Because even if ESC say that ESC acts as a Franklin rod, then you can have a copper rod. Maybe it's just a few hundred rands maximum if you get good quality, say 3-meter copper rod. Okay.
Thank you, Professor. Another question we have from Hamed Eghbali. Are there any advantages with ceramic lightning rod balls?
Minx, can you repeat what type of rods?
He's asking, are there any advantages with ceramic lightning rod balls?
Oh, now the thing is that if you say that, if somebody says that they have a ceramic rod, and if you ask me whether it has any advantages, what I can tell is that what ceramic are they talking about? Because look at the basics of lightning protection. We need to send a streamer to intercept with the step leader before the streamers from any other object is sent. So that we need a very good conducting material for the lightning protection system. If you can have a ceramic rod, which is as good as copper or aluminium in conductivity, and also it has the ductility and also the mechanical stability, mechanical and thermal stability, just like copper or aluminium, then it's okay. But my question is, what type of ceramic can provide this type of qualities for the ceramic rod to be qualified as a lightning protection system component? Okay.
Thank you, Prof. Our last question for today Is there sorry, it's from Tadala Malua. Is there anything specific from IEC 62305 series with regards to data centers?
Actually, if you are going for the data centers, yes, the IEC 62305 gives some idea, not just for data centers, but for installations that house electronics and so on. But usually for communication centers are covered in ITU standards, International Telecommunication Union standards, where the data center protection can be, you can adapt the ITU standard recommendations to protect data centers as well. It is not specifically mentioned in the IEC 62305, but you can get a very good idea about the protection of data centers from that.
Thank you very much, Professor. And for those questions that were asked and not answered, I will send the questions to Professor Gomes to answer, and it will be uploaded with the recording of today's webinar on the SAIEE website. So we've come to the end of our technical talk for the day. Firstly, I just want to thank Professor Gomes for availing his time to do this presentation to all of you and to me. And like I said, the recording of this webinar will be uploaded onto the SAIEE website tomorrow, as well as a copy of Professor Gomes's presentation. And within a few weeks, you will receive your attendance certificate with the CPD validation number. I thank you very much for joining us, and please visit the SAIEE website for upcoming webinars. Have a good afternoon. Goodbye.
Thank you very much. Goodbye.